Hi, welcome to the Security and Machine Learning session at today's Frontier in Machine Learning event. We have a great lineup of speakers for you today. Our first speaker is Aleksander Mądry, who's a professor at MIT, the director of the Center for Deployable ML, and faculty lead for the CSAIL MSR Collaboration on Trustworthy and Robust AI. He'll be talking today about what our models learn. Our second speaker is Dawn Song, professor at Berkeley and CEO and co-founder of Oasis Labs. She'll be speaking to us about AI and security challenges and the lessons we've learned in future directions. Dawn, unfortunately, will be giving her talk pre-recorded, but will not be here for the live Q&A afterwards because of family-related travel. Our third speaker is Jerry Lee, a senior researcher at Microsoft, and he'll be speaking about algorithmic aspects of secure machine learning. Throughout the event, feel free to add in questions in the chat, and we'll answer them during the chat or at the live Q&A at the end of the session. Thank you very much.
Hi, my name is Aleksander Mądry, and what I want to talk about today is what do our models learn? Okay, and as usual, this is joint work with my amazing students. So the point of start is the fact that, it's no surprise to any of us, namely that machine learning can and actually often is unreliable. Of course, one example of this is the notion of adversarial examples that we probably are all familiar with, but this goes beyond that. Of just, a month and a half ago, and we had this, the situation where on the highway, Tesla Model 3 crashed, without trying to even brake into an overturned vehicle. Probably what happened was that this vehicle was out of distribution for this, for the pilot, for the Tesla pilot, and that's what it essentially said. Okay, assume I don't know what it is, so I can just go forward confidently, and that's how the crash happened. So things are not always working the right way. And the question is, why does it happen? This is something I am thinking a lot, and my students are thinking about this a lot with me. And kind of one answer that we already came up with was that kind of at the root of all of that is certain mismatch. Namely, it turns out that if we look at all the tasks that we ask our model to solve, like all the classification tasks that we ask our models to solve, well, there turns out to be many ways to succeed at this task. And some of these ways, actually the best of these ways, might be different, actually very different, to how we as humans solve these tasks. Okay, and this kind of is at the root of many of the unreliabilities that we observe in the real world. And today, what I want to do is I want to kind of go back to this mismatch, but kind of consider it at a bit more meta level, namely in the context of so-called classification task misalignment. So let me explain what it is. So kind of the idea here is that usually when we think about supervised machine learning, we have always this view here that there is a data set, and then there is a model that we keep training on the data set, and we improve the model to get better and better accuracy. And this is this is exactly the bread and butter of machine learning nowadays, and that's kind of what we focus on. But kind of the point I want to make is that there is one element of all of this that we kind of usually don't think about. Namely, this element is that there is, in addition to the data set, there is actually a motivating real-world task, for instance, object recognition. And kind of our data set and the corresponding benchmark is meant to be just a proxy for this real-world task. And if you kind of think back to this missing piece, the question that you should start asking yourself is, okay, so if there is this motivating task that we really want to solve, and then there is just this projection, which is the benchmark we are actually trying to solve, is there maybe a possibility of us overfitting to this benchmark? And kind of this is exactly the question that I want to zoom in on in today's talk. Okay, so in particular, the question I want to ask is, how well our data sets reflect the real world? In particular, what data set biases do our models pick up? How are these biases introduced in the first place? And the point of start here, just to also give you some some kind of idea of what I'm talking about, I want to study these biases in a very simple setting, namely background biases. So this is joint work with my students Kai, Logan, and Andrew. And kind of the idea here is that, like, look at the simplest possible bias, namely how much the decision of a model depends on the background of an image, even though we ask it to correctly classify the foreground of this image. As we all know, our models definitely depend on such backgrounds. Okay, and that's actually not surprising because so do humans. Humans also use backgrounds when they solve the classification task. It's easier for you to recall who is the person in front of you if they are actually in the usual environment that you interact with that person. So if your work colleague, you would see them on vacations, it would take you a while to figure out who they are. Okay, so so we know that background is definitely a signal. So there is definitely a bias in our model. But the question is, like, can we get a bit better grasp of like how much of a bias it is? In particular, how much it differs, if at all, to how humans use this bias in their classification. Okay, to this end, we created this, just various version. Well, we took ImageNet and we kind of separated into the foreground and background signal and created a bunch of different versions of these data sets to kind of allow us to get a fine-grained understanding of dependencies between different types of background signal. And long story short, what we did, we just wanted to study how the model's performance is affected by different mixing and matching of this background signal. And in general, there was a bunch of findings that I will not have time to go over all of them in this short talk. But essentially, we realized that this signal really plays a major role in the performance of the models. And just one finding I wanted to bring your attention to is this notion of an adversarial background. So what we found that actually for most inputs, like over 87% of inputs, we can fool the model into wrong classification by just choosing the worst case background for this image. So the foreground picture is the same, and we just choose a adversarial background, and suddenly the model is fooled into misclassification of that foreground object. In fact, this gets even more interesting. Namely, it's not only that for most of the images there is an adversarial background, it's actually like some of the backgrounds are adversarial for many foreground objects. So here are just some examples. For instance, my favorite one is the one in the bottom left corner, which just shows that a person holding something turns out to be a very strong signal for the model that whatever is in the foreground is a fish, even if this is not a fish at all. Okay, so this kind of shows us that like things are not exactly as we would expect them. Again, humans use background, but they definitely wouldn't be fooled by that. So you might ask, what would it take to get models that do not have these problems? Okay, and in the paper we show that even just the simplest possible thing, like randomizing the background, during training, so essentially like breaking this correlation between the foreground and the background, already helps tremendously. And more importantly, even if you don't try to explicitly train against this, over-reliance on backgrounds, what you get is that, more accurate models, so essentially models that do better on ImageNet, also end up being more background robust. Interestingly, that doesn't mean that they don't rely on backgrounds. They actually do rely on background, but they rely on it in a way that actually makes it less prone to being fooled by adversarial backgrounds. Okay, so this was just a very simple example of a bias and the study of a fine-grained study of it. But now, we want to ask a broader question. So, okay, so there are these biases, but where do these biases come from? Especially, can we have biases that come from not just from the nature of the visual world, but actually from the way our data sets are constructed? And the spoiler is the answer is yes, but let's look into that. So essentially the point is that there is many biases that our dataset convey to our models. So just to give you, describe to you one of them that's particularly interesting, let's take a look at these 3 images from the ImageNet dataset and 3 ImageNet labels corresponding to these images. If you look at these images and in these labels, you probably will say that, okay, this looks like correctly classified ImageNet classifier, ImageNet input. However, what you will realize is that actually none of these 3 labels is correct according to ImageNet labels, and the correct ImageNet labels are now in the image. So this is kind of says, okay, so maybe we are not as good as humans and ImageNet classification as you would like to. But then you might think and saying, well, were these initial labels actually the wrong labels? If you look at the image on the left, it could equally be monastery or a church, and you can't really tell which one is which or which one is more right answers over here. So these are kind of just some handpicked examples of like the ImageNet labels maybe being a little bit kind of not exactly reflecting the ground truth of the image. But the question is, okay, so is this just just some outliers, or is it kind of significant? Does it signify some deeper problems with our ImageNet labels? Okay, so what might be the problem? And kind of when you look into it, you realize these are not outliers by any means. And essentially, kind of the issue here is the way our datasets are created. So kind of when we usually think about how our datasets are created, we think of this process when they are like real-world images, and then there are expert annotators that essentially choose for each image the perfect class to label this image with this class. So that's how we idealize this process, but that's completely not scalable. This is not how we can how we can get labels for millions of images. So what we do instead, like one of the most popular ways of doing it, is to kind of go the other way around. So what we do is we first settle on what are the possible labels we are interested in. And then essentially we source the images by just plugging this, desired class labels into search engines and getting all the candidate images for the given label. And then essentially, well, just to make sure that the images we source are actually really images corresponding to the desired label, we do the crowdsourced validation. And what we do essentially, we just, long story short, we just present this image to a crowdsourcer with a desired label, and we ask, does this image contain object of the class described by this label? And depending of whether the answer is yes or no, we either keep this image as correctly labeled with this label, or we discard it. So this is nice because it scales very nicely, especially when you ask these questions in batches. But the problem is that it's a very leading question. So we always ask only about the single candidate label for a given image. And we never make the human we are asking even aware that could be possible, like that could be some other classes that could be correct for the same image. So now this is a problem. This clearly introduces some bias. There is kind of some default label for the image. And if this default label for the image is not correct, then it's just discarded. And now the question, and this is the paper that we recently published, asks the question, okay, so how much of the problem this is for ImageNet? And the answer is, well, it is a problem, but how do we actually try to get a hold of this? Well, for now, to even get to perform any kind of study of these questions, you have to first get more detailed annotations, just because you need to confront the current ImageNet annotations against some more ground truth annotations over there. So how do you get them? Well, this is actually kind of tricky, but what we ended up doing was actually relatively simple, or actually surprisingly successful. What we did was essentially looked at a bunch of ImageNet trained models, and we kind of got the top 5 predictions from these models for each of the images that we considered. And this way we got a narrowed down set of classes that could remotely be plausible for this image. Now, once we manage to essentially get a small collection of possible classes for each of the images that could be the candidate classes, we just ask the MTurkers to essentially look at the image and ask them, okay, for each of these possible classes, would this label be valid for this image? And also we actually ask them about the information, to give information about how many different objects is there in the image, and also what would the main object in the image according to them be. And we did it, of course, we aggregated over many workers. And this way we got this very fine-grained ground truth annotations for for a subset of the ImageNet validation set. So this was actually exactly what we need for doing the step that I will describe in a moment. But I just want to point out that this is actually can be viewed as a nice bootstrapping of the original ImageNet annotations. In some ways, we got this initial ImageNet annotations that kind of got created in the way I just described, but then we kind of iterated on this via training models and then annotating using the labels generated by these models to kind of bootstrap this knowledge and clarify this knowledge and and distill it more. And we think that this process will be useful also in other contexts. But yeah, now that we have this ground truth label or more fine-grained labels, we can ask ourselves, okay, so how accurate the original image labels are? Well, we discovered a number of interesting phenomena. So the first one was the prevalence of multi-object images. It turns out that around 20% of test images contain more than one object. Here is one example. It's an extreme example that has really multiple objects, but there is like 20% of test images that actually have at least two objects in the picture. Okay, so how does it affect accuracy? Well, remember, like we ask our models to always answer just like we are talking about the top one accuracy. So we just want the model to output what is the correct label. And if it's wrong, we just say the model is wrong. So what it turns out is that actually, if you look at the accuracy of our standard models on the single label images, so images just with a single object, this accuracy is actually much better than what we view as the kind of state of the art. And only when you look at the performance on the multi-label images, then this performance becomes actually significantly worse. Okay, and what is even more important is that if we try to correct for this kind of obvious unfair situation when there can be multiple objects in the image, and what you essentially do, you make the prediction be correct if it matches either of the images, either of the objects in the picture, well, essentially this performance gaps disappear. And it turns out that essentially, whatever the current models are lacking in terms of performance on this multi-label images, it actually disappears and can be largely explained by just taking into account the fact that there are multiple objects in the image. So this is nice. And now the other question that kind of comes up in this context is saying, okay, if there are at least two objects in the image, you might ask, okay, so which one should the model answer if it's forced to answer, to choose only one of these objects? And kind of what we found out was somewhat surprising, that often the choice that the model makes is not the one that the human would make, particularly that the object that the model identifies is not the one that the human would view as the main one in the picture. So here are just some examples, and what's happening here is that since the image sourcing process of that we used to create an ImageNet was more willing to use this kind of more specific and unique labels for the particular images, because you get images as a response to your query. Well, our models also learned that this is the way to go, and they do pick up on these dataset biases, even though these biases go against human preference. So this is kind of another thing that we find in terms of discrepancy. And there's a bunch of other observations that we had, and I invite you to look at the paper to take a look at them. But the last question I wanted to ask, and that we ask in the paper, is okay. So once we have this correct ground truth labels, and once we have access to human annotators, we can ask how good ImageNet models really are, once we account for these issues with labeling. So particularly, we run this human-based evaluation, in which what we did is that whenever we presented a model with an image, and we got some answer, we did not just compare this answer against the ImageNet ground truth or against our ground truth labels even. What we did, we just asked the person, okay, here is an image, and here is a possible class. Is this class a valid labeling for this image? So essentially, we just ask humans to evaluate the validity of the labeling offered by the model. What did we find? Well, what we found is that the good news is that essentially, as our models improve in terms of just pure ImageNet accuracy, so does this human-based evaluation also improve. So far, so good. Our current driver of the design of the system seems to be aligned with the quality as assessed by humans. However, at this point, it turns out that annotators often can't tell apart the predictions of the model versus the correct ImageNet predictors. So in some ways, you can claim that at least for some classes, essentially our current models already hit the baseline of non-expert human annotators. And kind of this gives us a question, okay, so like how useful it is to try to improve the performance on the ImageNet further. Maybe essentially if non-expert annotators is our golden standard here, maybe ImageNet is already solved and we should be looking for some other data set and other tasks to kind of to try to improve our computer vision models further. Okay, that's all I wanted to say. So let me just summarize and talk about some takeaways. So first of all, I hope I made it clear that what models do and do not learn is not always clear to us, even though we kind of intuitively assume we do. And we really might need to study this before we focus on further improving performance on our current benchmarks. And this is particularly important if you think about robustness, because exactly like problems robustness emerge from these biases that are misaligned with the biases that humans use. Also, like as we showed, models are affected by biases of the world and of our data pipelines. And once we understand what these biases are, we can find ways to explicitly account for it. And there is some recent work with Jacob Steinhardt and my students that kind of show how to do it in a more refined form for some more subtle biases that arise in our data pipelines. And finally, moving forward, the question is, what are the other biases that our models learn from the data? And how do we train the models in their presence? Essentially, okay, for some biases, we actually might want our models to pick up on them. But for others, we might definitely not want our models to use them. And how do we kind of choose which one we do, which one we don't, and how do we enforce our models? How do we force our models to obey these wishes? And also, how do we measure, performance on the underlying task we care about, as opposed to just overfitting to this benchmark itself? Okay, so how do we do it in a way that actually really gets at the essence of the real world task we want to improve on, and not just an artificial number that's just a proxy, a mean to an end? So this is all I've got. Thank you, and I'm happy to discuss it during the Q&A session. Thanks.
Hi, thanks for being here. My name is Dong Song. I'm a professor at UC Berkeley and also the founder and CEO of Oasis Labs. Today, I will talk about AI and security, challenges, lessons, and future directions. As we all know, deep learning is making great advancements. For example, AlphaGo and AlphaStar have all won over world champions. And deep learning is empowering everyday products. As we deploy deep learning and machine learning, there's an important aspect that we need to consider, which is to consider the presence of attackers. It's important to consider the presence of attackers as we deploy machine learning for a number of reasons. First, history has shown that the attacker always follows the footsteps of new technology development, or sometimes even leads it. And also this time, the stake is even higher with AI. As AI controls more and more systems, attacker will have higher and higher incentives to attack AI. And also as AI becomes more and more capable, the consequence of misuse by attackers will also become more and more severe. As we consider machine learning in the presence of attackers, we need to consider several different aspects. So first, how attackers may attack the AI systems. Attackers can attack the AI systems for in a number of different ways. One, attackers can attack the integrity of the learning system, for example, to cause a learning system to not produce the intended or correct results, and can even cause a learning system to produce targeted outcome designed by the attacker. And also, the attackers can also attack the confidentiality of the learning system. For example, to learn sensitive information about individuals from the machine learning systems. And to address these issues, we need to develop stronger security in the learning systems. Attackers can also try to misuse AI and learning systems. For example, they can try to misuse AI to attack other systems, including finding vulnerabilities in other systems, try to devise new attacks, and so on. And also attackers can try to misuse AI to attack people. People are often the weakest link in a security system. We have already seen examples such as deepfake and fake news that actually can be generated from AI systems. To address these issues, we need to develop stronger security in other systems. So given the time limit of this presentation, I will mostly focus on the first aspect, how attackers can attack AI and learning systems and what we can do about it. And first, let me talk about the integrity aspect, how the attacker may attack the integrity of the learning system. And first, let's look at a motivating example. In the context of self-driving cars, for the autonomous vehicle, as it drives through the environment, it needs to observe the environment, for example, to recognize traffic signs to make correct decisions. These are photos of real-world traffic signs. Here, stop signs. And the second column shows a real-world stop sign example in Berkeley. And today's learning system can actually work very well and recognize these stop signs very well. As you can see, even when the real-world stop sign in Berkeley has some markers on the stop sign. But however, what if the attackers actually create specific perturbations to these traffic signs? For example, adding specific perturbations designed to fool the learning system, in this case, the image classification system, and try to fool the image classification system to give the wrong label. So in the third and fourth column here, you are seeing real-world adversary examples that have been created to then fool the learning system to give the wrong answer, in this case, misclassify the stop sign as a speed limit sign. So as you can see, adversary examples, when they are constructed effectively, they can fool the learning system to give the wrong answers. And one question that we have been exploring is, besides adding perturbation to digital images, can adversarial examples actually exist in the real physical world? And also, can they remain effective under different viewing distances, angles, and conditions? And here, the images here showing the examples of adversary examples that actually are created in the real world, and showing that in the adversary examples can actually be effective even in the physical world and can remain effective under the different viewing distances, angles, and conditions. And the real-world adversarial example traffic sign, the stop sign that we have created, have actually been on exhibit at the Science Museum in London, teaching people that it's important as we develop learning systems to pay attention that today's learning systems can be fooled by attackers and cause them to, for example, make the wrong prediction. So that's just one example showing that adversary examples can fool image classification systems. Other researchers and my research group, we have all been exploring this important phenomena across different domains in deep learning. And unfortunately, what we have found is that adversary examples are not just limited to image classification system, and in fact, they are prevalent in different types of deep learning systems, including different model classes and for different tasks, including generative models, deep reinforcement learning, and many others. And also, adversary examples can be effective under different threat models as well. Besides the earlier example I showed called white box attacks, where attackers need to know the details of the learning systems, including the actual model. The attacks actually can also be effective in what we call black box model. So in the black box model, the attackers actually don't know any details about the model itself, including the model architecture and the weights of the model. And our work and the other researchers' work have shown that adversarial attacks can even be effective in this type of model, in black box attacks. And we have developed different types of black box attacks, including zero query attacks, and where attackers don't even have query access to the victim model to be able to actually develop effective attacks on the victim model. And also, when attackers have query access to the victim model, attackers can develop even more effective black box attacks. So now let's look at a concrete example in one of our recent works. In this case, we are actually studying the deep learning model used for machine translation. Machine translation is an important task and has made huge progress. So in this work, we essentially showed two results. One is a state-of-the-art machine translation models. Actually, for example, that has been developed by Google and others. It actually can be easily stolen through the query access using what we call a model stealing attack. And as a second step, once we can steal the model, essentially build an imitation model of the original model, we can then develop adversarial attacks on this imitation model. And then using what's called a transfer attack, we can then use attacks that's been developed on the imitation model to then successfully attack the real world, the remote model. So in the first step, our work showed that we can actually very effectively develop this imitation model by doing a number of queries to the machine translation API in the real world. For example, with Google Translate and other cloud API services, we are able to build this imitation model that can achieve very close in performance to the original, for example, Google Translate and so on, based on standard benchmarks. And that's the first step. And then in the second step, using the learned imitation model, we can then develop adversarial attacks on the local imitation model, and then using the transfer attack to show that to demonstrate that these attacks that we have developed using the local imitation model, they can be effective on the cloud service, the cloud API, the real world model as well. And we consider different types of attacks. So here is a type of attack called the targeted flips. The goal here is to replace an input token in order to cause a specific output token to flip to another specific token. So for example, here we have an English sentence. I'm going to freeze. It's now below 6 Fahrenheit. Please help me. So with the Google Translate, with the original sentence, it provides the correct translation in German, as shown here. Using our attack methods based on a loss function that we construct, and using optimization-based methods, we are able to create an attack here by just changing one token here, changing from the 6 Fahrenheit to 7 Fahrenheit. When we feed this new sentence, I'm going to freeze. It's now below 7 Fahrenheit. Please help me. When we feed this input to the imitation model, then the translation mostly remains correct. But now, instead of translating it correctly to 7 Fahrenheit, it actually translates into 21 Celsius. So as you can see, this type of attack could cause severe consequences as they can be fairly stealthy and only change the important certain important parameters in the statement. And when we upload these constructed attack sentences to the actual Google Translate API, it shows that it provides the same translation results, showing that the attack is successful. There are other examples as well. So here, showing that we can easily create these nonsense sentence. For example, in English, it looks nonsense, but then when it translates through this machine translation, it actually translates into something that has real meaning, and also under the construction or specification by the attacker. So, for example, in this case, we can create this nonsense sentence, and then here in the first one, it translates into "I have to kill you," and in the second one, it translates into another, essentially a malicious, ill-meaning sentence. And again, when we feed these constructed attacks to the real-world cloud APIs, we see that the attacks remain effective. So these are examples demonstrating that also adversarial examples are not just limited to vision, they are also effective in, for example, natural language domain. And this really is a very rich field. There has been many different types of attack methods that have been developed based on optimization methods on different metrics beyond the L-norm metrics, and also including non-optimization based attacks. So for example, in some of our earlier work, we also showed that one can use GANs to generate adversarial examples as well. Overall, given the importance of this domain, there has been a huge volume of work and different types of approaches proposed for defenses against adversarial attacks. But unfortunately, for example, just in the last couple of years, there have been hundreds of papers written on the topic. However, today, still, we don't have sufficient defense today. Today, strong adaptive attackers can still easily evade today's defense. And what we have discussed so far is just the tip of the iceberg. It's in the general area of adversarial machine learning. Adversarial machine learning is about learning in the presence of adversaries. And attacks can happen at different stages of learning. One, it can happen at inference time, as adversary examples that I showed, that can fool the learning system to give the wrong prediction at inference time. And attacks can also happen at during training time. For example, attackers can provide poisoned training data sets, for example, including poisoned labels or poisoned data points to fool the learning system to learn the wrong model. Overall, adversarial machine learning is particularly important for security critical systems. I strongly believe that security will be one of the biggest challenges in deploying AI. And this is just the first aspect of how attackers may attack the integrity of the learning system. And attackers can also attack the confidentiality of the learning system by trying to learn sensitive information about individuals. Here, let's also look at a quick example. And this problem is particularly important as we know, essentially data is the fuel of machine learning systems. And a lot of this data is really sensitive. And hence, as we train machine learning systems, it's really important to ensure that the learning systems provide sufficient data privacy for individual users. In one of our recent studies, in collaboration with the researchers from Google, we set out to study the following question. Do neural networks actually remember training data? And if yes, can attackers actually exploit this vulnerability to try to extract the secrets in the training data and from just simply querying the learned models? And in our work, we showed that unfortunately, this is the case. So in particular, we studied the task of the language model, training a language model. And when we train language model, when we give a sequence of characters or words to the model will then try to predict the next character on the next word. And our work showed that in one example, we showed that when we try to train a language model using an Enron email dataset, which naturally contained actual people's credit card and social security numbers, and attacker, by just querying the learned language model, it can actually automatically extract the original user's credit card and social security numbers from just querying these trained models. And this demonstrates the importance of protecting users' privacy as even as we train machine learning models. And luckily, in this case, we have a solution. In this particular case, instead of training a vanilla language model, instead, if we train a differentially private language model, our work showed that the trained model actually can significantly enhance the privacy protection for users' data privacy. And at the same time, we can still achieve similar utility and performance. So given the interest of time, I won't go into the details of explaining what differential privacy is. It's a formal notion of privacy. And we also have done recent work in developing techniques and tools to automatically verify that a machine learning algorithm is differentially private. And the work called Duet has won the Distinguished Paper Award at the recent conference, Uppsala, a top programming language conference. Finally, I just want to conclude with another important topic related to machine learning, calling it a responsible data economy. As we know that data is critical to the modern economy, and given that a lot of the data is sensitive, so we are facing unprecedented challenges in how the sensitive data is being used. Individuals are losing control over how their data is used, and they are not getting sufficient benefits from their data. And also businesses are continuing to suffer from large-scale data breaches, and it's becoming more and more cumbersome and costly for businesses to comply with new privacy regulations such as GDPR and CCPA. And it's difficult for businesses to get access to data due to the data silos and privacy concerns. What we need is to develop new technologies that can unlock important values in data, but not at the cost of privacy. And hence, there's an urgent need for developing a framework for building a responsible data economy. This is something that my research group at UC Berkeley has been working on, and also we are taking some of the research technology into the real world at Oasis Labs. and in particular to build a platform for a responsible data economy by combining different privacy technologies as well as blockchain technologies to build a secure distributed computing fabric to enable users to maintain control of their data and rights to the data, and also at the same time to enable data to be utilized in a privacy-preserving way. And one of the first use cases that we will be launching using this technology is in the genomic use case to enable users to, for the first time, become owners of their genomic data, and also at the same time to enable their genomic data to be utilized in a privacy-preserving way. And also, we are launching a summit called the Responsible Data Summit. The first 2 tracks on responsible data in the time of pandemic, discussing how we can use data responsibly in this special time of COVID-19, and also how to utilize responsible data and technologies and develop responsible data policies in the real world. Please visit responsibledata.ai. So to summarize, there are many challenges at the intersection between AI and security. How to better understand what security means for AI and learning systems, how to detect when a learning system has been fooled and compromised, and how to build more resilient learning systems with stronger guarantees, how to build privacy-preserving learning systems, and how to build a responsible data economy. And this is in collaboration with many of my students, postdocs, and collaborators. Again, I strongly believe that security and privacy will be one of the biggest challenges in deploying AI. And building a responsible data economy is critical. These require community efforts. Let's tackle the big challenges together. Thank you.
Hello, in this talk I'm going to be covering a number of recent advances in the development of algorithms for secure machine learning. This talk is going to be structured in 2 parts. In the first part, I'm going to be covering recent advances in defending against attacks at train time. And in the second, I'll go over defenses against test time attacks. This talk is based off of a number of papers, some of which I've listed here. Okay, so let's just begin. So let's get started with robustness at train time. So there's a number of reasons why training data might be corrupted. For instance, imagine you're in some crowdsourced setting like federated learning where you cannot fully vet all of your data points, and there could be malicious entities adding in data to try to change the behavior of your learned model. Alternatively, another very common setting for scientists in particular is when you have very large data sets collated over many different labs and gathered by various different people using various different equipment. As a result, the data is very heterogeneous, and this can cause uncontrolled systematic noise, which can look just like outliers. And I want to mention this is really an issue in practice. A striking example of this is these so-called backdoor attacks, which Don might talk about, where adversary can add a small amount of carefully designed data to the training set, such that when a standard deep net is trained on this corrupted data set, this network behaves as if it's normal on regular data points. But when I feed in data with a pre-specified perturbation, like as you can see, for instance, like this flower or this sticker, the network misclassifies the image. Okay, so this for instance, a very big issue if you're trying to use this for self-driving cars or this kind of stuff. The fundamental difficulty, however, with defending against these attacks is that what it means to be an outlier is very unclear, especially when we go to high-dimensional data. In constant data, this is sort of the picture that we have for data, which is sort of like a bell curve, or at least relatively close to the mean, and not too spread out. So if the outliers don't want to be too obvious, then they can't be too far away from anything. And so usually they cannot affect any estimates or any classifier by too much at the very least. But this picture changes dramatically in high dimensions. So obviously I can't draw high dimensions here. But typically in high dimensions, everything, even the inliers, which are the blue points, are very noisy. So typically they're very far from the mean, and individually have very little signal to noise. As a result, the outliers can look individually just like inliers. So as you can see here, each one of the red dots looks just fine. But in aggregate, they can really mess up your classifier quite a lot. So that means somehow we must look for outliers at a much more global level. So this is something that was first considered by statisticians in the 60s in a field called robust statistics, which is something that really even predates modern machine learning. And it says that a data set is corrupted, or epsilon corrupted, I should say, if there's an epsilon fraction of outliers which corrupt basic statistics of the data. For instance, like the mean or the covariance. So the formal fair model is as follows. We have some data set represented by blue points, but we don't get to see this nice uncorrupted data set. Instead, we have to give it to a malicious and powerful adversary. And this adversary gets to look at the data and decide to change an epsilon fraction of the data however they choose. And this adversary is like all powerful. In particular, they have full knowledge of the algorithm and everything that the defender is trying to do. Then the data is returned to us after being corrupted, obviously without the colors. And then our goal is to learn statistics or information about the original uncorrupted data set, for instance, the mean or the covariance. Unfortunately, this is a pretty difficult problem, at least for a long time, especially in high dimensions, because for over something like 50 years, all methods for high-dimensional robust statistics, overgeneralizing slightly, either were computationally intractable in high dimensions, or had error, which scaled really poorly as the dimensionality increased. So essentially, you either just couldn't run the algorithm, or you could, but the output you get is just meaningless. Okay, this was finally broken, actually, in 2016, when my collaborators and I, along with concurrent work of Lyra and Paula, were finally able to break this curse of dimensionality by giving the first polynomial sum algorithms for some of the most basic problems in robust statistics, particularly robust mean estimation. At a high level, the idea is that if we can detect corruptions to the mean, we can detect corruptions to the mean by inspecting spectral properties of higher order moments. Pictorially, the picture is as follows. So suppose we have this corrupted data set where the blue points are the inliers and the red points are the outliers. And the true mean is supposed to be this blue X. But because of the outliers, has been dragged over here. Well, in particular, notice that along the direction in which the mean was moved, there must be a lot more action than there should be, just because all the red points are sort of in aggregate kind of pushing in this direction. In particular, the data is supposed to be spherical, but because the bad points are dragging in this direction, this causes a lot more action than there should be in this direction, and so the actual covariance is rather than spherical, more like elliptical on this direction. And formally, this manifests itself as a large eigenvalue of the empirical covariance. So I can't get into too much details for the sake of time, but from like 1,000 feet in the air, this says that the more that a single data point contributes to large eigenvectors or eigenvalues of the covariance, the more outlier-like it is. We were able to measure this quantitatively by devising a score function based on something called quantum entropy regularization, which allows us to measure this in a principled manner. So I'm going to flash some equations here, mostly just to make myself feel better. But you don't need to really understand this. But the point is that these scores, which are the tau i's, are things that you can really easily compute in like near linear time. And if they're larger, then the points must contribute more to like being outliers. I should say that this is actually formally used in our paper to get really fast algorithms for robust mean estimation, particularly nearly linear time algorithms. But by themselves, they're already just useful as an empirical tool for outlier detection. Okay. And we can measure this. We measure this in a number of basic settings. Again, I don't want to get into the details, although I'm happy to take questions about it offline. And we found essentially that these empirical quantum entropy scores, these quantum entropy scores were just consistently better at finding outliers in a number of settings. So here are some plots I'm just going to flash. ROC-AUC is some sort of measure of how effective the method is at detecting outliers. And as you can see, we consistently do better on this task than previous methods. In particular, if I could draw your attention to the plot on the right. So in particular, ours is much better against all these previous benchmarks. And this is also true in another setting, which again, I don't really want to get into too many details about. Okay, but that's the high level idea. And I should say I've only covered just a little bit of sort of this sort of wave of current work on data poisoning, but there's been a lot of exciting progress in this field that I can't cover. So for instance, we've had provable defenses against stochastic optimization, which is a task that generalizes training stuff like deep nets, as well as practical and provably robust algorithms for many other objectives, not just mean estimation, as well as empirical defenses based on sort of these same ideas that we've developed for these backdoor attacks that I mentioned at the beginning of the talk against deep networks, and much more. Okay, but that's all I really want to say about that. Now let's pivot to robustness at test time. So as Aleksander has presumably already discussed, adversarial examples are a well-documented phenomena in deep learning. Namely, it's well known that you can take an image, any image, and add imperceptible changes to the pixel at test time, and you can cause a standard neural network to reliably misclassify the image. And I want to stress that while this was first developed in academic context, this is not just an academic concern. So this is something that happens in the real world and can be carried out in a number of different settings. So here are some pictures. For instance, they can cause stop signs to be misclassified as speed limit signs, or cause facial recognition to misclassify people. And sort of, you can imagine the security vulnerabilities of all these sorts of things. Now, broadly speaking, there are two types of defenses that have been proposed against these attacks. The first type of attack is empirical, two types of defenses, not attacks, that have been proposed. The first type of defense is empirical, namely defenses that seem to work well in practice, that we don't know how to attack, but we don't know how to prove work. However, many of these have been proposed and then subsequently broken in like weeks or months of publication. So there's a sort of cat and mouse game here. One notable exception to this is the adversarial training framework of Mądry et al., which to date is still unbroken, and if I had to guess, likely is genuinely robust, but again, we can't prove it. But to try to break this sort of cycle of attack and defense, another paradigm is that of certifiable defense. And these are defenses which provably cannot be broken. However, they usually pay something for the certifiability. In particular, a lot of these defenses that have been proposed don't scale or get much worse numbers than empirical defenses. However, one recent and very promising approach that might bridge this gap is something called randomized smoothing. So the idea behind randomized smoothing is very straightforward. The formal definition is here, but again, I don't want to get into the formulas. More pictorially, you can think of it as the following. Suppose that this picture is the surface of your classifier, so that every region with a color is a region of space that's classified as one class. So all the blue points are classified as one class, all the cyan points are classified as another, and so on and so forth. But this is your base classifier. You then want to smooth this classifier. So given a point x, the smooth classifier samples a bunch of random Gaussian points centered at x and counts what fraction of them fall into each region. The corresponding histogram that you see is the likelihoods that the smooth classifier assigns to each point. So here, notice that the smooth classifier still assigns the blue region as the most likely class for x after smoothing, but this is not always the case. So the reason why we care about randomized smoothing is that recently there's been a line of work culminating in this paper by Cohen et al., which proved the following very strong robustness guarantee for any smooth network. Again, for the sake of time, I don't really want to go into the details, but at a high level, it says that if your smooth classifier is very confident at a point x, then your smooth classifier is also robust for some L2 radius or some L2 ball around your point x. Okay, but again, I don't want to get into too many of the details here, but it just says that all you need to do is you need to train a smooth classifier to be very confident at a point, and if your smooth classifier is very confident at that point, then you have robustness to adversarial perturbations sort of for free. But this is not a trivial task. How do you actually train networks such that the smooth classifier is effective? What if, if I add Gaussian noise to my data, and all this pattern, all these nice patterns and everything are destroyed? Turns out you can do okay. So Cohen et al., the paper I mentioned already, does pretty well already with some basic Gaussian data augmentation, a very classic technique anyways. But in recent work that appeared in we showed you can do much better, namely by combining this framework of randomized smoothing with the empirical defenses of adversarial training. And particularly, we showed that by directly robustifying the smooth network using adversarial training on some sort of smooth loss, you can train the network such that the resulting network is much more certifiably robust, which is kind of nice because by combining certifiable defenses with empirical ones, one can dramatically improve certifiability, which is not at all clear a priori, right? Since the empirical defenses come with no guarantees whatsoever. And again, for the sake of time, I don't want to get into too many details, but you can see here briefly that indeed our method dramatically improves upon the previous state of the art. And indeed, this is kind of cool. Sometimes our certifiable accuracy, so our provable accuracy, is even higher than the empirical accuracy of the previous smooth networks, which is something that, it says that our network is just genuinely much, much stronger. Okay, so these are results in CFAR10. Again, I don't want to get into too many details about these results. We also have results for ImageNet. And actually, by combining our techniques with other heuristics, like pre-training or this kind of stuff, you can even boost these numbers even higher. Okay, but so far this has been all about L2. Now what about other norms like LP? Particularly, L infinity is a sort of standard benchmark for adversarial examples, and norms like L0 or L1 correspond much more closely to adversarial patches, which are these like real-world attacks that we saw earlier in this talk. However, Gaussian smoothing is no longer effective for these norms. Gaussian smoothing is very much tailored for L2. So how do we try to attack this problem? In work that's to appear at ICML this year, we, with many caveats, begin to characterize optimal smoothing classifications for many other norms. So we begin to develop this theory of how to do randomized smoothing much more generally. So from the upbound side, we give formal methods to derive, again with caveats, sort of quote-unquote optimal sampling schemes for arbitrary norms based on geometric objects such as Wolf crystals, which is some object that arises naturally in physics, as well as some other methods, which I won't get into. And from the lower bound side, turns out you can actually show very strong lower bounds, demonstrating that randomized smoothing has inherent limits, at least current techniques for it, for a number of norms based on this sort of rich theory of geometric metric embeddability. So in particular for L infinity, the best you can do is actually just pretend that, embed L infinity in L2 by losing this root D factor, and then use Gaussian smoothing. So that's kind of neat. Okay, and this sounds pretty, abstract, but turns out you can actually show that these methods yield improved certifiability compared to the prior state of the art in practice. So here are some results where you can show, by using these smoothing techniques that we developed before, and then just trying them out, just trying these smoothing distributions that we tried out, you can actually dramatically improve the previous state-of-the-art numbers up to 20 or 30%. So despite the fact that this is, uses some very rich mathematics, very deep mathematics, it's actually just very easily practical, or very, I should say, yields dramatic improvements in practice as well. Okay, so that's pretty much all I have to say. Just to wrap up, let me just say that this is, this field of algorithms for secure machine learning is a very new area of study, and many new algorithmic ideas are still needed to overcome many security issues that we face in practical ML. Okay, that's pretty much it. If you have more questions, I'd be happy to answer them at the Q&A. Thanks.
Hi, and welcome to our live Q&A following our Security and ML pre-recorded talks. With us today for this live session is Aleksander and Jerry Lee. So we're going to be taking questions via the same chat interface, so feel free to add in any questions you want to for either Aleksander or Jerry or both, and we'll talk through them here. To get things started, I wanted to ask both of you about a question that was touched on briefly in the live chat during your talks. I'm curious, if you would say a few words about how you would define robustness, kind of in the ideal way. Some mentioned defining it based on, for example, how a human would behave. What's your take? Let's start with Aleksander.
Sure. As I already said in the chat, this is a great question, and there is no good answer. So in some ways, like I think just part of the reason why there's no good answer is that, like, to us, robustness means so many things, and we try to pack it into one definition. So yeah, so one definition that kind of much of my work is focusing on is saying robust means robust to whatever human would be robust to. And this kind of makes sense in the context of, of vision or sounds. And that's one definition of robustness. It's a very difficult definition of robustness because it's essentially like, if we wanted to take it to extreme, we would need to essentially solve like AGI, because you would need to have synthetic humans. But then there is the other definition that we kind of, it's closer, that I think we don't think enough, but we should, especially in the domains like system security or any domains where humans are not the golden standards we want to attain. And then this question is just robustness means providing some invariances that we would like our model to obey. Okay, so for instance, like we just want to know that if if there is a stream of packets, actually this might or might not be a good invariance. If we kind of, move the timings of each a little bit by not changing the order, it should not affect the performance. So essentially, this is like different kind of priors we embed into our model because we know that, they should not be material for the decision. So this is the whole new definition, which is it's just about that. But yeah, what robustness means is really like in the eye of the beholder.
Yes. How about you, Jerry? What do you think?
Yeah, I mean, I think Aleksander is completely correct. There really is no one complete definition of robustness. I should say that, adding on to what Aleksander was saying, I think in large part what we do, or the stuff at least that I work on, is understanding like how to make models robust to misspecifications in the model when the data distribution has some sort of drift. And this drift can be because of either attackers or just because of natural data drift. And so this is another way we can think about things, which is also just, I guess, that's another way of rephrasing this idea of building in invariances. But it's a very difficult question.
Let me just say one more thing is that it's a very difficult question. So like as if all the difficult questions, we should try not to, confront it head on. Instead, we should just try to look at concrete context and some like small pieces of it. And that's how we build the intuition and hopefully a generalizable toolkit. So, let's not despair right away.
Yes, we don't have to boil the ocean all at once. We can start small and understand specific situations. I totally agree with you. Yeah. Kind of related to this, I guess, definitional questions. There's also some discussion about threat models. And I think I'll start with you, Jerry. How do you start to think about the different kinds of threat models, and how do you choose which ones to focus your work on? What kind of benefit do you think you get by switching between different threat models from time to time? How does that help you?
So this is very much related to the question that we just asked, because certainly developing a threat model against which we need to be robust is really the question of what does it mean to be robust. From this perspective, I think it really depends on the motivation of the problem, or the context of the problem. Suppose I'm trying to make a network robust in some real world setting. I need to understand what sorts of attacks one might actually care about in that setting. Or if I'm just trying to make some sort of algorithm robust, outliers to training time, what are the outliers going to be? Or like what kind of realistic constraints can I impose on the outliers? So this is sort of, I think, the way that is most natural to me seems to be that we need to take a very context specific approach to this, try to understand, what are the actual constraints that might matter in practice, and then try to build back from that to get a realistic theory.
So where do you both get your motivating contexts, the specific application scenarios you decide to go to? Where do they come from? How do you decide which ones are most exciting to you? Aleksander?
Sure. So yeah, so that's a great question. And like, so I have two strategies. Well, this is a part of the same strategy, but there are two kind of modes. So one mode is I want to focus on an application that really matters. Like, much of my work is about deployable ML. Like, what happens where we deploy ML in the real world? What kind of challenges arise? So you choose some use case and just try to see what will be the first thing that you will hit there. Like, what will be the major problem? And once you identify this problem, you try, of course, always to clean it up. So you can actually try to study it in isolation, model, and benchmark. And that's essentially one way we come up with like part of my work. The other one, so this is the work about kind of trying to understand exactly the definitions of robustness and how to even know that our ML model is robust. And then the other strand work is about developing the toolkit. And for that, I just choose the simplest threat model that kind of makes this toolkit sweat. So like there are this infamous LP robustness things, which yes, of course, it's clearly just a tiny piece of what robustness would mean, but it's a great kind of very analytically nice threat model to work with if you want to think about developing tools. Because even getting this LP robustness is difficult, and it forces us to think about techniques, approaches, and in particular randomized smoothing came from that. So these are the two modes. So we kind of alternate. We either think about relatively simplistic, rudimentary notions of robustness to improve our toolkit and understanding of robustness as a phenomenon. And then there are like much more attuned to specific use cases kind of studies where we kind of try to see what new facets of robustness we can discover through these events.
And just to add on to that very briefly, even in this case where you have like these very context-specific things, I think it's important to still distill them back into like simple to state, very basic problems that are like fundamental that we don't understand how to attack or how to defend against these sorts of things.
So I'm looking at the chat window, and I see a couple of technical questions coming up. So I wanted to ask one, not technical, slightly deeper questions. We're seeing often today, and this is paraphrasing Saeed's question, we're seeing often today that that today's models and methods have a bit of a trade-off between model robustness and accuracy. Do you think that that trade-off is fundamental, or do you think that that we just haven't gotten the right methods yet?
So yeah, well, given that much of my work is about exactly this trade-off, so this trade-off is fundamental. Like in some ways, it's a trade-off between specialization and generality. So in particular, like our current ImageNet model, they get better accuracy than humans in some ways on this specific distribution that ImageNet corresponds to, because the models are able to figure out all the idiosyncrasies of the data sets and kind of get great predictors. So, but yeah, we know it from the real world. Like if you specialize, you lose on generality. So the trade-off is there. Of course, the question is how much of a trade-off it has to be. Maybe it is possible to like make this trade-off be almost non-existent for many of the data sets we care about, and that's essentially what we are thinking about. It's kind of how to get robust models with better natural accuracy, so it's less painful. But the trade-off is fundamental. It just kind of you can show many ways in which kind of sometimes if you just care about very specific distributions, there are things you can do, like just for backgrounds, like I talk in my talks about backgrounds and foregrounds. Again, if you just care about specific distribution of images, then actually you should be looking at background, because background may be very telling of what the correct answer is. But unfortunately, if you think about robustness, then this might not be a best idea to look at the background. So there is this trade-off is there naturally. So yeah, that's the answer. Jerry, do you have anything you want to add?
I think pretty much I would say the same thing as Aleksander. I think certainly, mathematically you can demonstrate there are trade-offs between trying to be robust, trying to get accuracy, just because the objectives there are not the same. The question really is like how much of this manifest in practice, and we see this like to varying degrees. And I guess the hope is really to try to narrow this gap as much as possible in practice. I think that there's been some encouraging work that has been trying to narrow this gap in a number of settings, but it's still there for now. And yeah, it's definitely inherent, but I guess it's just how much, to what degree it has to be there in practice.
Yeah, and just one point I want to make, in some ways, like we say, it's robustness between robustness and accuracy, but it kind of, we should ask ourselves what accuracy really means, like in the end, like, is even this accuracy bought by kind of, exploiting some like strange idiosyncrasies of distribution, even the accuracy we want, right? Like, even though it, like the number is high, but is it even the object recognition we are looking for? So again, so this is kind of a question that we should be also confronting.
So I guess that's interesting. So not only do we need to be careful about our definition of robustness, but also our definition of other performance measures like accuracy.
Yeah.
Well, I think the two are closely tied. Sorry, go ahead.
Oh, go ahead.
I mean, I feel like the two are closely tied. Like, robustness means robust accuracy, but what does robust accuracy mean? So.
Yeah, and I would add, I guess, given that we're talking about security and robustness issues, I guess safety is another measure that might differ from accuracy, but also need careful definition. One of the lively topics that came up during the Q&A for your talk, Aleksander, was one that's that I feel very passionate about as well, and that's causality and causal machine learning. I was wondering if you could say a few words about the connections that you're seeing between robust machine learning and causality, and maybe a little bit about the problems that you're seeing. Like, what are the challenges in getting these two, I think, methods to work together to solve these types of issues? Where do you think that they haven't quite fit together yet? Where are the problems remaining?
Yes. So as I said in this chat, in some ways, to me, lack of causality, of embracing causality, incorporating causality into our, machine learning models, like, and talking about vision in particular, is one of the roots of the problems that we are observing. And in some ways, essentially, currently our deep neural networks, they are like amazing correlation extractors. So I usually call this like correlation extraction. This is like a double-edged sword. On one hand, this is what enables these models to do all of these impressive things, but this is also exactly like, all the things that like we come up, oh, this model did not do what we expected them to do, or they did something ridiculous. Like, you very often can, essentially tie it back to the fact that, the model interpreted like a correlation as a causal relationship. So in some ways, like, trying to interpret causality in our models is exactly the way to go. Now, the problem is that in some ways, like, much of the work in causal learning currently, it's in a very different setting. It's kind of in a setting of where we exactly know what are the factors that we kind of want to try to model the causal relation between. And this is definitely not the setting where vision is in. So we had discussion over the chat, so currently the only approaches to, providing causality is, I would say, in a reactive form. So essentially, like, we think of interventions, like we say, oh, if I change this background to a different color, I know, like, according to my, causal model inside my brain, I know it should not change the outcome, but it does. So this is clearly an evidence that the causal model, inside the model is different to one that it should be. So kind of you can do this these reactive things, except the problem is, how do you come up with even interventions to pinpoint this point? So we have some in our work, we show that for robust models in vision, you can actually like gradients towards different classes show an interesting ways to come up with this kind of interventions on which you can say, oh, the model is thinking this is a dog for this reason. And now we see why it's kind of like this is wrong. So in particular, there's like plenty of interesting spurious correlations that we learn as we work with the models. Like, for instance, that we learned that for a crab, the natural habitat is a plate, right? Because like images on the web, many people just photograph crabs on the plate. So anyway, so clearly this is needed, but like, it's hard for me to have a very precise and principled framework about this. Again, it's more about like when we see something wrong, we can phrase it in this language, or there's an intervention, it had an effect, but it shouldn't. But like, it would be nice to be kind of more predictive, but I really don't know how to do it. Like as a beginning, you would need to have much more fine-grained annotations. So we can even talk about object that there is like, I don't know, there is a hat in the picture, there is, a blue background and something. And, before, like, we have to even know what are the objects we should be reasoning about first. And and we don't even have that. So that's even like that's what makes this problem much difficult. But like we have to think about this.
Yeah, I guess if I was to rephrase, I think it's the challenge of learning the feature representation at the same time that you're reasoning about the causal influences. And obviously, how you choose to represent what's in the image influences how those representations are influencing each other.
Yes, exactly. And in some ways also like part of the problem is that like the features you come up with might not directly kind of correspond to the abstract kind of factors that you would see in the picture as a human. So yeah, so that all makes all of this difficult.
Yeah. There's one philosophical issue that I keep seeing coming up in discussions of computer vision causality. That's a simple one of whether the object that you're trying to label is causing the pixels, whether the pixels are causing the label. And that seems like, given that the direction of causality matters so much, right?
Yeah. And that's a great question. So like honestly, like when I get too frustrated about this, I just come back to this reactive approach. I'm just saying I know when it goes wrong, and that's all I care about. So like I just want to get a model when I cannot find an intervention that makes things go wrong. But again, this is not a very comprehensive or really like it's not a solution. It's just a patch.
Mm-hmm. Jerry, what do you think is the most kind of promising directions in solving some of these problems algorithmically? We've been talking about causality. Do you think that that's one of the main promising directions? Do you have others that you've been working with that you think are key to making progress on these issues?
I guess I would sort of split the defenses and sort of responses to attacks sort of into two buckets. There's sort of like the short-term horizon kinds of things. These are things that you can imagine and engineers and real-world practitioners could be using, within a year or something like this to at least make attacks, if not impossible, but at least more difficult to implement from the attacker side. And I guess here, this is very different, I guess, from causality, which would be, I think, one of the more long-term horizon sort of approaches. And I think in the long-term horizon, there's like many different algorithmic approaches that could actually yield good defenses. For instance, randomized smoothing could be better, or maybe better adversarial training. These are all very promising, but I think getting them to be deployed in the real world within maybe the next 3 years or so is probably still would require some additional work, because there's a number of practical overheads that go into any of these academically developed defenses. But in the more short term, I think the more promising things are things which are more like system security interventions, less so like actual machine learning, but more like applying these system security principles, like sanitizing input as much as you can, these sorts of things. Yeah.
Well, that's a great actually segue into a question that I wanted to ask both of you, and I'll start with you, Jerry, since you mentioned it. The question is this: how much of the issues and the solutions to the general challenge of security and machine learning do you think are going to come from algorithmic advances themselves versus either being more data-driven, coming up with the right data sets and training methodologies, or crafted application scenarios that help us get around the most difficult aspects of threat models? Jerry?
So I tend to think that, at least while, as I mentioned, these short-term interventions are useful, they're not likely to be truly robust, in the sense that you're probably going to be able to get around them if you're a sufficiently dedicated adversary. It's not clear if you can actually really ever hope to get it with a truly robust system, because again, we don't really know what that is. But at least you could hope that in the long-term horizon, these more algorithmic advances could give you much more principled defenses that actually sort of more broadly work in a more sort of principled fashion. So I think hopefully it'll be a mix of the two, I guess, but I don't know. I guess we'll see.
Yeah, so just to avoid answering this yes or like one or the other question, like I really like, because again, I'm thinking about these things a lot, and again, it's very frustrating in many ways. So like kind of like I like to tie it back to other aspect that we usually talk about, but somehow this time it didn't come up with, is the explainability. Like in some ways, like I think one of the goals of everything you should be doing is just understanding, what makes our models tick. And, at the very least, if we can't make it, do it what we think it should be doing, we at least should know in which way it fails and kind of how to reason and engineer around this. So to me, this is what is great about the algorithmic thinking, is that it kind of, you can start kind of diving into like exact way, like how things should work. And then of course, you need to, to figure out the divide, like it's never perfect, but kind of at least it forces you to think in a like kind of prescriptive way. But like, in the end, I just don't know. Like at this point, I really kind of like much of my work currently, and I started from this like let's build these defenses to get like robust AI and everything will be great. But essentially, like what much I do is I can realize, okay, this is more complex than I thought, and kind of I'm just now more of trying to understand how these things fail, and kind of what makes this model tick, and kind of can we at least like open up this black box and see what's inside, so we can like kind of regroup and think about the solutions there.
I also want to just briefly add, I think it depends a lot on the context. So for instance, I think we've been talking primarily in the context of adversarial examples where algorithmic defenses have been quite hard to come by. But in other contexts, for instance, data poisoning, I think there's been a lot of great work recently in developing, well, I guess a lot of work that my collaborators and I have been doing that seems to be developing really, practical algorithms that do offer a very strong guarantee of robustness to data poisoning attacks. So I think it also depends on the context quite heavily.
I was just smiling. I saw a great comment in the chat window just now. Aleksander commenting on the fact that you recently released a image data set where all the backgrounds were replaced, and now you yourself are speaking with your background replaced as well.
Yes. So as you see, like, so like no one got fooled that I am in some like galaxy. So I guess it doesn't really work, but I guess the model would believe that I'm somewhere inside, outside of in the cosmos. But yeah, it doesn't work.
Yeah. I believe we're in our last few minutes. Do you have any last words you'd like to say, Jerry?
I mean, I think just that this is still a very interesting field for sure. And there's it's a very interesting field because there's a lot of interesting philosophical questions here that we've been sort of skirting around constantly that have real world ramifications, which are very interesting, as well as some really interesting mathematics going on here. So it's like a really interesting like intersection of all these three sorts of aspects of the field. And a lot of interesting work still to be done, I guess. I hope.
Yeah, so I cannot agree more with Jerry. Like, I really have a lot of, like, in some ways, if you hear my answers, I say, we can't do this, we can't do this, we can't do this. So it sounds like a very frustrating kind of type of research to do, but I actually have an immense fun. And in some ways, like, really what was funny is that, like, I came into this field from like a purely optimization point of view. Then I started to think about the security. But now, kind of as you dig deeper into this problem, you start thinking about, what even learning means. You start thinking, how ML is used, how it should be used. You start thinking about biases, about fairness, and all of this. And it's really like inspiring to see like how this like simple problem that you start with forces you to kind of embrace. Now I'm talking to neuroscientists and thinking about neuroscience and brain. So like I really love this research area because yes, it has big questions that I don't expect to solve anytime soon, but it really pushes you to study very interesting math, very interesting, different sciences, and just think about the society and the world. So, if these are the things that you enjoy thinking about, I think it's hard to find a better field than this.
I agree with you. I think that's one of the things that I find super exciting here is just the opportunity to think about these systems and what we want them to be doing and how we can get them to do that end to end. It brings up so many cross-cutting issues. So speaking of cross-cutting issues, I'll take a moment to, now that as we're ending our session, I'll take a moment to just mention to our audience that we're going to be going on a half-hour break now from 12:30 to 1 p.m. Pacific time. And at 1 p.m., the Frontiers in Machine Learning event will be back with a panel on Beyond Fairness, Pushing Machine Learning Frontiers for Social Equity. The moderator will be Mary Gray, and the panelists will be Radit Abebe, Irene Lowe, and Augustine Chanteau. So please join us in half an hour for another really interesting session. And right now, I'd like to thank our panelists, Aleksander, Mądry, Jerry Lee, and Don Song, for joining us today. Thank you very much.
Great. Thank you so much. It was a pleasure.
Thank you.